we are going to talk about today is two rigorous statistical tools for objective analysis of quantum random number generation. Just to elaborate a little bit, getting a little bit ahead of myself. So basically, in this study, I performed two experiments to understand if the quantum random number generation quality is better than that of classical random number generation. What we mean by quantum random number generation is having a quantum machine, although in this study we didn't use a quantum machine, but a quantum simulator running on a classical Turing machine for the quantum aspects of the experiment. And as a comparative, we had the Python library NumPy on the classical Turing machine for the classical random number generation, and we performed two experiments with this apparatus and setup to essentially understand and eventually conclude that quantum random number generation is consistently better in quality than classical random number generation. So having given that a little bit of a background, let me go ahead to the next slide and look at today's agenda. So here's today's agenda. We have introduction section, which I briefly touched upon right now. Followed by that, we'll have a work conception and coverage section, which essentially puts in perspective the current work with respect to what was performed as a scope in this endeavor, and then we'll talk about how this approach is new in terms of what has been attempted already by the scientific community. Then I'll take a little bit of time to describe the two experiments that I have performed and present some substantiating visual evidence, and then I'll go over the apparatus and the results from both the experiments that we got, and then conclude for this session. So having mentioned that, let me go ahead and get into the introduction. So bear with me for being verbose on the slides, because it, a little bit of late notice, but that's fine. So I'll be brief. The statistical evaluation of random number generation is known through the works such as that of Wherein, wherein one of the methods utilizes the p-value test statistic. Now, a p-value is a meta-statistic that indicates the degree of randomness in a given sample of generated random numbers. And in this work, I have extended that notion of the degree of randomness or quality of the random numbers to compare based upon the p-values, the random number samples that were generated from the Qrng with those derived from the CRng. And the way I performed the experiment is that I had random number generation both from the quantum simulator as well as the classical NumPy library, and I fed the random numbers so generated into a evolutionary program, and essentially looked at the convergence as we shall see in figuratively in the following slide. So like when this experiment was performed, the evolutionary program converged more favorably in terms of favorably and quickly in terms of providing a solution to two of the mathematical equations which also I will show. It converged better with the quantum random number generation and was objectively analyzed by the p-values, and the p-values indicated that this was indeed the case. And then, once that was achieved, we wanted to have another source of information to validate what was performed in the first evolutionary program experiment. So I went ahead and performed another experiment using topological data analysis methods, to verify the consistency and integrity of the results and conclusions obtained with the evolutionary program. Now, to describe this topologically data analysis experiment, the raw random numbers again were generated from the quantum random number generator simulator and the classical NumPy Turing library. And the two samples were compared by a TDA program, topological data analysis program, in which essentially I obtained the phase space representation of the random numbers generated by taking the takens embedding. These are a little bit, I'm not going into details of the topics, but I'll point to references which essentially show what was the attempt that was made with the topological data analysis. The phase space representation of the quantum random number generators was evaluated by a the phase space was evaluated by comparing the distance, the bottleneck distance, which is a standard distance in statistic, between the quantum random number generator simulator and the classical NumPy library. And it was indeed found that the results and conclusions were inconsistent with the first experiment, the other evolutionary program experiment, and that was the conclusion of the study, as we shall see shortly. Having said that, let me navigate to the work conception and coverage. So the present work is envisaged as a beginning of the objective analysis and interpretation of applications of Qrng to solutions of problems in different realms, like trying to solve. This is a preliminary work for which can form a basis for a randomized solution of randomized partial differential equations, classifications of evolutionary algorithms, Fourier and Newtonian method implementations, and the works you see. So this work leverages the superior computing capabilities of the exalogic machine, as I will show in the apparatus setup, to the quality of random number generations with the quantum simulators running across variants of Turing computing hardware, as demonstrated by the two different experiments performed. Having said that, what is new in this approach? So basically, we didn't find any scientific work that directly applies the comparative techniques of the p-values. As I mentioned, there are references in the literature where p-values have been independently used for evaluating the quality of random number generation. However, a comparative approach to the Qrng versus the classical RNG is based upon comparison of p-values has not been found or attempted. and also, as I said, the consistence of this result with the other experiment, the topological data analysis experiment, is also not found. So that's what is new about this work here. Having said that, I'm just describing the first experiment in which the evolutionary approach was used to solving two mathematical functions, which I mean the rastrigin and rosenbrock functions, which are presented over here with the parameters that they have, and so what was fed into the program that implements these functions was that random candidate solutions, which is mathematical or numerical analog of the gene pool in biological processes. These solution candidates are evolved by mutating and thresholding mathematically. What I mean by that is that a sample of random numbers is generated again from within the generated input set. Three random candidates are picked up. They are mutated by applying a mathematical operation and thresholded with respect to the error that is obtained on with the three mutants. And if the threshold exceeds a certain limit, then we inject that candidate into the solution pool and evolve the solution pool. Once the solution pool is evolved, what happens is that we again compute the loss function for the error or the loss function, and then determine if the new set of solutions is closer to convergence than the original set, and then we iterate for the next generation and so on. And as I will show, as I mentioned, mathematically and I mean pictorially, what happens shortly, and then and this way we find the convergence in the first experiment and input that data for the p-value analysis and find that the p-values for the quantum random number generation are half those those obtained for the classical generation, and which essentially means that Qrng is better in quality, as I mentioned again, this will be substantiated by the second experiment, and I'll describe the second experiment again here. Yet another experiment utilizing the methods inspired from topological data analysis is performed. In this topological data analysis based comparative experiment, random numbers are generated both with Qrng and CRng paradigms, and as I mentioned, the phase space for the generated samples is obtained by taking the standard Takens embedding of the random samples. Now that you can have references, I can point to the references, or if you have questions, we can take that up. So the Takens embedding gives the space space. The space space is nothing but a plot of the x and y values along with the evolvement of evolution of the samples in terms of the differential coefficient, and this is what is essentially a Takens embedding of the phase space representation is. I'll show it again, this also pictorially. And once that Takens embedding is obtained, then the bottleneck distance, again, these are standard statistical methodologies. So the bottleneck distance between the Qrng and the CRng samples is computed, and essentially found that, again, in consistence with the first experiment, it's found that the Qrng, has a smaller distance range than the CRng, which has exactly the double distance range between different runs of the program. And therefore, we can extrapolate and say that, well, yes, from the two experiments that we performed, quantum random generation is indeed better in quality than classical random generation. And as mentioned in the results section, the same what I just mentioned, a discussion in the logical result interpretation from both the experiment emphasizes the experimental proof of the fact that Qrng surpasses CRng qualitatively. Now I'll present some sample visuals as I just mentioned. So this is a sample visual of the Takens embedding, which is the phase space of a sample of Qrng generated. This is how it looks, and this is basically the X and Y coordinates representing the values themselves, and the Z coordinate is the differential. The maximum and minimum. The value of the differential coefficient at that particular XY coordinate. That's what is the Z coordinate in this Takens embedding. Having said that, this is for experiment number 2, and for the experiment number 1, this is a sample pictorial of how the Qrng in the evolutionary program converges. The x-axis is the number of generations that in the experiment that I described, and the y-axis is the candidate individual, the index of the candidate individual, where the error function, the loss function was minimized. And you see that after a certain period, the algorithm converges, and exactly where the x coordinate is 11, you see that there is no further perturbation obtained in the sample by taking the thresholding and the mutation. So that's where the convergence and these points of inflection are fed into the p-value statistical analysis, and just like I mentioned, the results are obtained. And this is just for the record of what apparatus was used for classical and quantum. For the classical, we use the Python and the NumPy library, and for the quantum simulation, we use the Python and the Q#. Q# is the quantum simulator from Microsoft. And that is, in summary, a description of the apparatus that was used. And essentially, for the topological data analysis, experiment number 2, we use the Python. The version is mentioned over there, and the Godi library, which is the version is mentioned over there. The Godi library was utilized to compute the bottleneck distance, which is the standard distance. And so I'm presenting the results from both the experiments. The Qrng conversion point is 11.7.5. and I mentioned the X and Y values, what they represent, and the Turing convergence point is 12 and 15. You can see that it's in terms of the number of number of generations, consistently for both rastrigin and rosenbrock, the number of dimensions for the Qrng is exactly half. You can see for the rosenbrock also 7 and 14 you can compare. Again, this is about the second experiment, the Qrng bottleneck distances. The bottleneck distance, as I mentioned, was computed from the Godi library. And you see the range here for the Qrng is between 17.5 and 27, whereas the range for the CRng is in the almost double range, where you have 57 to 38 to 57 as the ranges that come out at different runs of the experiment. So essentially, I concluded by comparing p-value 0.3541 between the two quantum groups and the p-value 0.1083 between one quantum and one classical group shows consistently that the quality of random number generated by quantum sources is higher than the classical sources. It's exactly half. Establishes the conclusion that the results, now this experiment was also performed in one of the original works where the hardware was the Windows PC, and in this study that was carried forward with the Exalogic computing platform, the high performance computing platform was employed, and the results were consistent across that as well. And results from experiment 2, the bottleneck distance, again, just to summarize, the range of the bottleneck distance is obtained for Qrng is half than those obtained for the CRng. There is a certain extension of this work which I'm evaluating and considering with respect to the topological distances, but that will be a further work, and we'll be going from there. So here are a couple of references for all the works that have been incorporated here. And I again want to thank you, and that's my name and email address if you guys want to be in touch. And I can open up for questions now if we have any from the audience. Thank you. Questions from the audience?